Powerful cycles are shaping the planet, and we have no control over them. In this video, you'll learn about the massive shifts currently taking place that will impact our lives, so stick around until the end. Welcome, everyone. Everything will change time and again because there are several cycles, some of which span thousands of years. Some of these cycles take place in space, for example, the movement of our solar system around the center of the galaxy. Then there are the Milanković cycles, which, among other things, cause the Earth's axis to wobble due to gravitational influences within the solar system. Other cycles are entirely terrestrial, such as the weather phenomena El Niño and La Niña, which alter the climate of the entire planet, or the cycle of our Earth's core, which is still virtually unknown to us. What is clear in any case is that all these cycles inevitably determine our fate. Let's start right off with the big picture. How does our solar system actually move through the galaxy? Earth races around our home star at an average speed of 30 kilometers per second, and most depictions of the solar system are limited to this movement of the planets around the sun, but that is by no means all, because we must also take into account the movement of the entire solar system within the galaxy, the Milky Way. Our Milky Way is our cosmic home and consists of at least 100 billion to 200 billion star systems. Our solar system is one of them, and all these stars are engaged in a kind of galactic dance, a rhythm known as the galactic year. They orbit the center of the Milky Way, and it takes our solar system 225 million years to complete one orbit. So at the beginning of this galactic year, dinosaurs still existed on Earth. Although the planets move around the sun, they follow it on its path around the center of the galaxy. But the universe doesn't end behind our galaxy. There are billions of other galaxies, and most of them are arranged in so-called galaxy clusters, which in turn form superclusters. Within our galaxy cluster, the local group, various galaxies and dwarf galaxies are gravitationally attracted to one another. The strongest effect here is the gravitational pull between our Milky Way and the even larger Andromeda galaxy. The two are hurtling toward each other right at this very moment and will merge into a super galaxy in a few billion years. So we also have to factor in our approach to the Andromeda galaxy when calculating our motion. The two galaxies, and we as part of the Milky Way, are moving toward each other at about 109 kilometers per second. But as mentioned earlier, there are other galaxy clusters as well, and they also influence us with their immense gravitational pull. The other galaxies and galaxy clusters near us all exert a gravitational pull on us, and even distant clusters of matter in deep space still exert a gravitational force. Based on our calculations, all these distant structures together seem to cause an additional motion of about 300 kilometers per second. However, in a slightly different direction than the other motions. But there is another force at work that almost no one is aware of, and it is caused by the vast emptiness. For every atom or particle of matter in the universe that is concentrated in an over-densified region, such as areas where many galaxy clusters are found, there are also regions that have lost the same amount of mass. And these regions therefore exert less gravitational pull. When there is a large area of space with less matter than average, the absence of gravitational pull acts as a repulsive force. In our cosmic neighborhood, opposite the location of the largest supercluster near us, there is a vast low-density void. Since we are located between these two dense regions, the attractive and repulsive forces add up, each reaching about 300 kilometers per second, resulting in a total of around 600 kilometers per second. If you add up all these motions, that is the Earth's rotation on its axis, the Earth's orbit around the sun's motion around the galactic center, the motion of the Milky Way and the Andromeda galaxy toward each other, and the local group, which is attracted by the over-densified regions and repelled by the less dense ones, you get a figure that indicates how fast we are actually moving through the universe at any given moment. And this overall motion is 368 kilometers per second in a given direction, give or take 30 kilometers per second, depending on the season and the direction in which the Earth is moving at that moment. Moreover, this motion can also be confirmed by measurements of the cosmic microwave background, that is, the high-energy radiation dating back to the early universe. The cosmic microwave background appears warmer in the direction we are moving and cooler in the direction opposite to our motion. But if we no longer take our solar system as a reference point, but instead, for example, the local group, we can then calculate that our group of galaxies, that is the Milky Way, Andromeda, the Triangulum Galaxy, and all the dwarf galaxies, is moving at about 727 kilometers per second relative to the cosmic microwave background. so it all depends on perspective. No representation is entirely correct or entirely incorrect. Our solar system is thus a sort of cosmic ball, tossed about in all directions by all sorts of gravitational influences. Let's take a closer look at our Sun, a gigantic fusion power plant to which we are, in principle, completely defenseless, and of course, the Sun's behavior has a massive impact on Earth's climate. The Sun's magnetic field arises from complex flows of charged particles occurring within the Sun's interior. Although this magnetic field is surprisingly weaker overall than Earth's, it is nonetheless of great significance for processes in the solar system. The Sun undergoes an approximately 11-year activity cycle known as the sunspot cycle. During this cycle, the number and intensity of sunspots appearing on the Sun's surface vary, a phenomenon closely linked to the solar magnetic field. As solar activity approaches its peak, a remarkable phenomenon can occur, a solar pole reversal. This means that what was previously the Sun's magnetic north pole becomes the south pole and vice versa. This is accompanied by increased sunspot activity and a higher probability of solar flares. These flares in turn can hurl enormous amounts of charged particles and high-energy radiation into space, thereby affecting what is known as space weather throughout the solar system. In December 2024, for example, a gigantic hole formed on the Sun, from which high-energy radiation was fired toward Earth. So that's the solar pole reversal, but the same thing can happen on Earth too. We too have a magnetic field, and it acts like a kind of invisible force that protects us. It extends from the interior of our planet far out into space and plays a vital role in shielding Earth from harmful cosmic radiation and the solar wind. Without the Earth's magnetic field, the high-energy radiation from space would roast us, so that complex life on Earth likely would never have emerged. The Earth's magnetic field is generated by the Earth's dynamo, that is, currents of liquid iron and nickel in the Earth's outer core, which lies beneath the solid Earth's mantle. These currents generate electric currents, which in turn generate the magnetic field that surrounds the Earth. This magnetic field has a north and a south pole, which are usually located near the Earth's geographic poles, but not necessarily exactly on them. The Earth's magnetic field is anything but static. It undergoes continuous change over time and can even reverse itself. During such a pole reversal, the magnetic field goes through a period of instability in which the polarity reverses. However, the process is much slower than on the Sun. On Earth, we're talking about thousands of years. During this time, the Earth's magnetic field weakens and may even exhibit locally weaker spots or multiple poles before finally reaching its new orientation. This can have massive effects on Earth because, as the magnetic field weakens, more cosmic radiation strikes the Earth and is also directed to other locations. This can then paralyze all technology and, depending on the intensity of the radiation, also lead to significant health risks. Researchers believe that the pole reversal is relatively imminent on a cosmic scale because the magnetic North Pole has been moving faster and faster in recent years. In addition, a magnetic anomaly has developed over the southern hemisphere, the so-called South Atlantic anomaly, a weak spot in the magnetic field that is becoming increasingly pronounced. Some researchers interpret this as evidence of an impending pole reversal. In summary, the solar pole reversal is a short-term event linked to the 11-year sunspot cycle. It is directly related to activity on the Sun's surface and sunspots. The Earth's magnetic field reversal, on the other hand, is a long-term process spanning thousands of years. This process is linked to the flow of liquid iron in the Earth's outer core and has no direct relationship to solar activity or the solar magnetic field. It is also clear, however, that the Earth and the Sun are magnetically connected. The Earth's magnetic field is constantly influenced by the Sun, and the Sun's activity even influences much larger processes far beyond it, such as the exact size of the so-called heliosphere, the region in which the Sun displaces the interstellar medium through its own radiation, thereby creating a protective bubble in which we travel through the galaxy. And therefore, one of the most exciting effects of the solar pole reversal is its influence on the interplanetary magnetic field. When the Sun reverses its poles, this change spreads throughout the entire solar system. The interplanetary magnetic field, which carries the solar wind, is also affected by this reversal, and this can cause the interplanetary magnetic field lines to change, altering the interactions between the solar wind and the magnetospheres. The strength and characteristics of the Earth's magnetic field are thus directly influenced by these processes on the Sun. The theories that changes in the solar magnetic field can influence the Earth's magnetic field by shaping the cosmic radiation that reaches Earth, and that this in turn affects Earth's climate and geological processes, are incredibly fascinating but have actually been little studied. However, based on current knowledge, it is unlikely that a solar pole reversal would trigger a pole reversal on Earth. It is not just the sun, but the entire structure of the solar system that influences Earth. This is summarized in what are known as the Milanković cycles, an incredibly complex topic that has, however, had a massive impact on life on Earth since the very beginning. To understand this, let's first quickly explain how the seasons we are familiar with actually come about. Earth rotates as it orbits the sun. However, its axis is not quite perpendicular to this orbit. The Earth's axis is tilted by just under 23.5 degrees. As a result, one part of the Earth is tilted toward the sun while the other part is tilted away. These varying angles of sunlight incidence create the seasons. In most depictions, this is limited to the Earth's movement around the sun, but this is highly incomplete because there are many more celestial bodies in our solar system, and they all interact with one another to a greater or lesser extent. Although the sun accounts for 99% of the solar system's mass and is thus definitely the strongest gravitational influence, the gravity of the other objects also affects us. The moon, of course, but also Jupiter, the heaviest planet, Saturn, and to a much lesser extent the other planets as well. They all pull and tug at one another, and this affects our Earth, specifically the tilt of the Earth's axis, the exact shape of our orbit, and the ecliptic plane, the plane of the planet's orbits. All these factors are subject to complex yet regular cycles due to physical influences within the solar system, and these are the Milanković cycles. The Serbian mathematician and geoscientist Milutin Milanković was the first to recognize this in the 1920s. So we're talking here about several astronomical cycles that have a massive impact on our planet and the climate, and despite this immense importance, the average person has likely never heard of them. Perhaps the most important Milanković cycle is the elliptical cycle. Over a period of 100,000 years, Earth's orbit around the sun becomes less elliptical and then more elliptical again. Logically, the less elliptical the orbit is, the more constant the temperature on Earth. When the orbit becomes more egg-shaped, there are severe temperature fluctuations and the maximum temperatures in both directions become more extreme. Currently, summers tend not to be particularly hot and winters tend not to be particularly cold, as we are currently in a more circular phase of the Milanković cycle. If the Earth's orbit becomes more elliptical over the next 10,000 years, these seasonal trends will intensify and winters and summers will reach much more extreme levels. But it's not quite that simple, because there are other Milanković cycles, such as the precession cycle, which affects the Earth's axis. We've already noted that the Earth's axis is tilted by 23.5 degrees and that this is what creates the seasons. As part of the precession cycle, the Earth's axis performs a kind of circular motion, and this takes 26,000 years. That's also why, by the way, the North Star isn't always the North Star. A few thousand years ago, the Earth's axis was pointing in a completely different direction. In just under 13,000 years, summer and winter will switch places in the respective hemispheres. There are countless other Milanković cycles, some less significant, some more. And the interplay of all these cycles leads to something that is as strange as it is frightening: ice ages. Some of the Milanković cycles align perfectly with the ice ages in Earth's history. For example, a cycle in which, over the course of 100,000 years, the Earth's orbital plane around the sun rises and falls relative to the solar equator. Exactly how this triggers ice ages isn't entirely clear yet, but the timing fits so perfectly that scientists are convinced there's a connection. One theory suggests that on its steeper orbit around the sun, the Earth passes through a cosmic dust cloud that blocks some of the sunlight, leading to significantly lower average temperatures. This means that it is only a matter of time before the Earth changes its orbital plane as part of this Milanković cycle, average temperatures drop, and an ice age awaits us. Here, one final Milanković cycle comes into play, and it will very likely bring us the ice age. I'm referring to the axial cycle. The axial cycle causes the Earth's axial tilt to change. The 23.5 degrees we just heard about are also unstable. During the axial Milanković cycle, which lasts 41,000 years, the Earth's axial tilt varies between 22.1 and 24.5 degrees. We are currently in the part of the cycle where the tilt is decreasing. The result? No part of the Earth is tilted toward the sun anymore. The ice that forms in winter then barely melts in summer. The more ice there is on the Earth's surface, the more sunlight is reflected back into space rather than absorbed. This is a self-reinforcing process that ultimately leads to an ice age. We are currently living in a brief warm period, also known as the Holocene interglacial, a brief exception with a mild climate that began just under 12,000 years ago. So this is a brief anomaly within a larger ice age, and thanks to the Milanković cycles, this anomaly will eventually come to an end, and the ice age that is actually currently prevailing will regain the upper hand. That could take several millennia, however, which is of course not long at all, from a geological and cosmic perspective. And of course, we must take into account that human activities are known to have an impact on the climate as well. As for the relationship between the anthropogenic greenhouse effect and the Milanković cycles, we are still very much at the beginning of our research. To wrap things up, we're heading deep into the Earth's interior. The Earth's core is still incredibly mysterious and unexplored, and when scientists discovered that we're receiving a signal from down there at regular intervals, they were quite astonished. It all began in 2019, when Chinese researchers from Wuhan measured some very strange readings in the Earth's core. They found that there is a fluctuation that occurs roughly every 8.5 years, which could be described as a wobble of the core. Overall, the Earth consists of three main layers: the crust, the mantle, and the core. These layers have different densities and possess distinct chemical and physical properties, which are influenced by geological processes such as plate tectonics and volcanism. The Earth's core is the innermost layer, consisting of iron and nickel and maintaining a pleasant temperature of about 5,500 degrees. The core is divided into two regions, the outer and inner core, with the outer core being about 2,300 kilometers thick and liquid, while the inner core is solid and has a diameter of only 1,200 kilometers. Previous models assumed that the Earth's core rotates along the same axis as the Earth's mantle, since both layers were thought to have a uniform density distribution. But now we must forget all these ideas about the Earth's interior, because what the Chinese researchers have discovered is quite revolutionary. By precisely mapping tiny changes in the Earth's rotation, they arrived at a groundbreaking explanation. The Earth's core could actually be tilted at an angle to the mantle. Specifically, the Earth's core is tilted 0.17 degrees relative to the mantle. Hao Ding, one of the lead scientists on the new study, explains the results of the Earth's free oscillations suggest that the density structures inside the Earth are highly heterogeneous, so the assumption of a uniform density distribution is unlikely to be realistic. One of the most exciting conclusions from the research is the hypothesis that the Earth's inner core is denser and heavier in the northwestern hemisphere than in other regions. And it is precisely this asymmetric distribution of density and mass that could explain why the Earth's core appears to wobble every 8.5 years. Ding says, this implies a differential rotation angle of the inner core of less than 1 degree to the east, and a misalignment of the axis of symmetry of the boundary layer between the lower core and the upper mantle. Done. And that has truly massive implications for numerous other processes on Earth. Take the Earth's axis, for example. If the Earth's core does indeed wobble every 8.5 years, and this wobbling motion is accompanied by an inclination of the core relative to the mantle, that could indeed affect the stability of the Earth's axis. A change in the inclination of the Earth's core could theoretically lead to a change in the inclination of the Earth's axis over time. But in recent years, the Earth's axis has also been behaving extremely strangely. Since the mid-1990s, its drift has changed dramatically. It shifted about 10 degrees to the east. Scientists have been quite at a loss as to why, but perhaps this new research is the missing piece of the puzzle, and the movement of the Earth's axis can be attributed to the curious processes occurring inside the Earth. And then, of course, there is also the potential impact on the Earth's magnetic field. As we already know, the Earth's magnetic field is mainly generated by a dynamo-like process in our planet's outer liquid core, which is driven by the movements of the liquid metal. And we also know that this magnetic field is crucial for life on Earth, as it protects us from harmful radiation from space. If the Earth's core wobbles every 8.5 years, and in the process the density or mass distribution within the core might even change, this could obviously have consequences for the currents in the liquid core and thus directly influence the dynamo process and the Earth's magnetic field. One possible effect could be a change in the strength or direction of the magnetic field, and that in turn could affect animal navigation, the operation of electronic devices, and the spread of cosmic radiation. Furthermore, the wobbling of the Earth's core could also lead to instability in the magnetic field. I could imagine that these new properties of the Earth's core play at least some role in the strange behavior of the magnetic field in recent years. As a reminder, the migration of the magnetic North Pole has been intensifying in recent years. Scientists interpret this to mean that the magnetic field is becoming more fragile and is approaching a pole reversal. The so-called South Atlantic anomaly, a weak spot in the magnetic field, is also becoming increasingly pronounced, all signs pointing to the magnetic north and south poles preparing to switch places. And perhaps the rhythmic wobble of the Earth's core is also a piece of this geomagnetic puzzle. I hope you are now absolute Earth cycle experts. As soon as any of these effects become noticeable on Earth, I'll let you know right away. Of course, you'll only get that if you follow the channel, so please subscribe now. Feel free to check out the next video as well. As always, it's turned out to be super exciting. You'll also find the Astro Shop in the bottom left corner, where you can stock up on the right items for every cycle. Otherwise, I'd say see you in the next video. Take care.